So let us see what happens with horizontal circles. For this example, we will have a ball with mass m attached to a string and sliding along a circle on a frictionless horizontal table. The radius of the circle will be r. Um, on the table, there will be a hole drilled so that the string can actually go through that hole and attach itself to a block with the mass little m. The question in the problem will be how fast should the disc or the ball spin on the table so that it can keep the hanging block suspended or from prevent it from falling down. So let's look at the ball on the horizontal table first. Here's the ball. There's a string that provides tension and keeps the ball along the circular motion. Here's the vector for that tension. And of course, that tension is the only force acting in the horizontal plane, given that the table is frictionless. So the tension is the force that serves as the centripetal force and creates that acceleration, the centripetal acceleration pointing towards the center of the circle. We see the two vectors for the tension and acceleration are parallel to each other. It is not convenient to draw an axis here. It's kind of hard to determine whether it's going to be x or y axis, given that axis is going to be rotating because we'll be working with a radial direction. So you can draw an axis if you wish, but you have to remember that axis has to be rotating together as one with the ball so that it's always aligned with the tension and with the acceleration. It's a little bit tricky to picture, especially if it's the first time you have seen this situation, but nevertheless, Newton's second law really leads to a very simple equation here for the radial direction of this motion. We are going to apply it here for the radial components, which will give us that the tension, the radial component of that vector tension, has to be equal to the mass of the ball equal to the acceleration of the ball. Remember that the acceleration is the centripetal acceleration, so it has to be equal to v squared over r. Let's see what happens on the other end with the block that is hanging from the rope. Here we have gravity pulling it downwards and tension holding it up. So if we want that block to be suspended, in other words, it's not going up or down or falling down, then we need the acceleration of that block to be zero. So applying Newton's second law for the vertical components of the vectors here on this diagram, we get the following equation: plus t minus mg has to be equal to 0. So I see here that my equation is very, very simple. It simply tells me that the tension in the rope has to be equal to mg. That's actually somewhat of a trivial result. We could have seen it immediately without going through all those proper steps, but nevertheless, it's a good exercise. Physically, what this means is the tension has to cancel gravity if we were to keep that block from falling. So I can take this result and use it here for the previous equation, which will give me that the little mg, that's the mass of the hanging block times the gravitational acceleration, has to be equal to the big M, which is the mass of the ball, times its speed squared, v squared, divided by the radius of the circle r. Or little mgr over the big M has to be equal to v squared. And there it is, my answer for the speed with which the ball needs to be circling on the table to keep the hanging block from falling. V must be equal to square root of little m gr divided by the large M. Sometimes here students ask questions: what happened to the gravity and the normal force on the ball on the horizontal table? Well, they're there. Here it is. The gravity still points down and the normal force points up. I didn't want to include them here simply because they don't contribute to the solution of this problem, and I didn't want to distract you from the solution. But in case you wonder what happened to them, they're there. And you can certainly apply Newton's second law for the y components of the vectors. Remember, the tension and the acceleration have no y components, so they won't be contributing at all in that equation here. So I will have only plus n minus mg has to be equal to 0, or that the normal force will be equal to the big M times g. So you can see how this, while it's interesting and it's good to have there for completeness, really doesn't contribute to the solution of this problem.